Thank you, Yuni, for the introduction. And first of all, I want to thank Win, or now called Quant QNC, for giving me the opportunity to come here to share our recent work with you. And I think I just want to give a very introductory talk about the research work we are doing at NRC, partly because I'm looking for university collaborations for our research activities. So I want to go to very details of the specific topic. But if you are interested, you can always talk to me or send me email for more details. And so I will give, by the way, how many of you are familiar with printing technology? Okay, so quite many. And so I will give a very brief introduction about printing technology, and we talk about NRCCP activities. And then I will really give a few examples of difficulties in PE. Instead of saying how wonderful the PE is, I will say how difficult it is to really use that as technology, and what are the solutions towards those difficulties. And then I'll talk about a little bit is the PE application in making autonomous power supply for mini sensor systems. So printable electronics had a big impact, or had very big wave a few years ago, because everybody thought that we will be able to use printing technology to make a lot of electronics, like printing newspapers. So the idea is to combine the functional inks with the printing technology to make RFIDs, logic circuits, etc. So at a very low cost. So at that time, everybody thought that's a transformative opportunity for adding intelligence to printed media. Okay, but that's still the case. But how we see this opportunity, how to use it, is very different. So about 5 or 6 years ago, NRC put $45 million down, and with $15 million money from industry, we formed a Printable Electronics Flagship program. The idea is that the purpose is to grow the ecosystem in Canada and create wealth for Canadians. And actually, we are quite successful in creating this ecosystem. Right now, you see the Canadian, the Printable Electronics Association has gone into IntelliFlex. We have close to 45 companies in the system. And so when we're talking about printable electronics, everybody is thinking about flexibility, a large area, and low cost. And those advantages give us a chance to dream about the application of these devices in like smart packaging, smart labeling, etc. So NRC formed that PE program, and my group is one of the thrusts we call the functional devices. Our responsibility is to print, to design, fabricate, and characterize all sorts of printable devices. So the main expertise in my group is organic semiconductor materials, metal oxides, and in application OPV, OLEDs, etc. And metals. And we have some expertise in surface interface chemistry and physics. And we learned how to printing. Before this program started, we had no experience at all in printing, only in spin coating and inkjet printing. So over the past 5-6 years, we worked on a variety of printed devices. And for example, we worked on printed high precision resistors for multiplexing device for smart drug packaging to detect when the patient take the medication, and record it, send the message to the system. So this technology was developed together with Jones Packaging in London, Ontario. And we have developed the printed organic FET matrix sensors, like breathing sensor, heart rate sensor. And we also developed printed antennas for e-passports and printed solar cells, printed photodetectors, and the different type of energy harvesting devices using piezoelectric and triboelectric effects. So we have acquired a series of printing equipment like the Dymatic 5000. It prints on 50 centimeter by 50 centimeters substrate, and with a positioning accuracy of like 1 micron. So you can use that system to print pretty high resolution transistor arrays. And then you have a screen printing system and a multifunctional system. You can use that as a gravure, flexo, and rotary screen printing. And we also recently acquired one aerosol jet printing system. And these are very individual, like a sheet printing system. And we designed together with a company in Switzerland to have this sheet-fed multi-station printing system that allows us to print on the lesser size substrate, but using different printing technology with very high layer-to-layer alignment accuracy for semiconductor device fabrication. And here what we can do is that we can share the drying station and the curing station because the sample will be moved, will be transported on the platform from one printing station to another and to drying station. So in that, the difficulty is in roll-to-roll printer. A lot of people say that printable electronics, we can use roll-to-roll printing at high speed. The problem is that when we print organic semiconductor devices, you are not printing graphics, the same base material, but with different pigments. So the curing time in that case is fixed. You say, okay, 20 seconds under this light intensity, or 110 degree, 20 seconds. But when you print organic devices, you have a very wide range of annealing temperatures, curing conditions. So if you want to do roll-to-roll printing, it's actually very, very difficult. Every time when you change a device, you have to change the oven length and the lamp, everything. So in our case, we put the sample is movable from station to station, and we can use the curing station or drying station. You can control temperature, high and low. You can have a different dwell time for device fabrication. So it's actually very ideal for making multi-layer semiconductor devices. And this is a system in Montreal for the ICI they have. But if we really want to go to roll-to-roll printing, we can go to Montreal to use that system. But that system is not easy to use because you have to figure out all the printing conditions first. Otherwise, you have to waste a lot of material. So before that, it's the best way to do this sheet-fed printing system. So we have a series of printing systems with, of course, that will give you different type of printing speed, resolution, and the film thickness you can acquire. But when you look at those systems, they have different names, different type of printing mechanisms. By the end, it is a system that allows you to dispense functional inks to different locations you want to put, right? With define the resolution, volume, and accuracy. So, but when you look down to the bottom, how to make printable devices is you need to, you will find a way how to turn functional materials into usable inks first, and how to print them, then how to achieve the functional film after they dries up. So when you make functional inks, you have to have a good printing properties, and then you have to have good film forming properties. And after dry up, they need to retain the physical properties you want in that either polymer or nanoparticles you designed at the beginning. So it's not always the case. And also, how to solve layer-to-layer solvent compatibility issues. Because in graphics industry, when you print, you rarely care about the layer-to-layer interaction. You care about lateral interaction because when you print color prints, you put the 3 colors side by side, right? Occasionally, when they make multi-layer printing, this is to make the top layer look the most beautiful layer. That's their purpose. They don't care too much the interface between each layer. But when you make organic devices or semiconductor devices, the interface is a very important property in your device fabrication process. So you need to consider all these control factors when you design a fabrication process. So most important process, of course, is interaction of that ink with your substrate. So at the beginning, that's why I said, as I discussed before, at the beginning, people are really hyper about this, about printable electronics. So we think we can do a lot of things with it, almost parallel with the silicon device. It's a basic. By the end, it's almost not possible. We have to find the right application for printed electronics, right? So first of all, when you print metals, for example, up to now, there's no one metal ink can provide the conductivity the same as the metal bulk metal. So that's not almost impossible. And they are always more resistive than the bulk metal. Another thing is the line profile. When you print, dump your ink on substrate, you will have all sorts of profiles. If you are working in that, my background is semiconductor physics. When you look at these awful profiles, you know you will have large variation in resulting devices. It's impossible you want to design the circuit using this thinking the same way as integrated circuits in semiconductor technology. And then the line width, the printed electronics, the printing technology or printing equipments were designed for graphics industry before. We know our eyes can't tell difference between anything like below 100 microns, right? Our resolution is at that limit. So all the equipment, the layer to layer, dots, alignment, accuracy, is somewhere between 50 microns to 100 microns. So once it runs, you will see that's perfect prints. So all the equipment you can acquire on the market, that'll give you at least 50 micron, almost 50 micron layer to layer alignment accuracy. So how to make the device like high density, high resolution semiconductor device? Because we are talking about 10 micrometers and below, but the alignment accuracy is 50 micron above. So you have to find a right way to do it. And this is an example. Like if you have source drain electrodes, you want to align this gate to the channel. If that's below 50 micron, you will miss the channel, or you have to print a bigger gate to overlap that area. But you have very large parasitic capacitance to slow down your device frequency. And then another thing is the compositional variation in thin films. When you print, when it dries up, the composition will vary from the top to the bottom, depend on the composition of the film. One typical example is printed metal ink. You say, okay, I have very high conductivity ink because those inks were formulated for lateral conduction, like for printing your microwave oven control panel. What they care is from A to B. But if you want to use that ink to make your transistor, you are talking about vertical conductance. But there's a phase, typically in most of these inks, there's a phase separation when it dries. The bottom layer is typically more resistive, actually. So when you do the transistor measurement, you have to reformulate the ink, right? Because they are meant for the lateral conduction. Not, traditionally, they don't care about the vertical thing. They want to have the passage around the surface. So those things present challenge you make when we make organic semiconductor or printed electronic devices. So now, I said that we have those strong. We have to think about interaction of ink and substrate, because that's a very basic interaction between the matter you print on substrate, print down, and your device. Okay. So one thing I will show you is a very basic phenomenon is coffee ring. A lot of people know that. When you drop a coffee on on the table, on the glass, it dries up. You see a dark ring outside in the outside ring, and lighter in the middle. So all the coffee nanoparticles, micrometer particles, migrate to the edge of that. Because when a drop of ink wets the surface, the three-phase interface, the air, substrate, and the liquid, that area dries up first. It pins the interface. And when the liquid dries up, the dome structure pushes down. You have a capillary effect to push these particles towards the boundary. So by the end, you put all the particles around the boundary, and that's why you see a stain ring called coffee ring. And that coffee ring, but there's a way to control the drying process, right? You can either make these particles different shape. They can mobility along the surface can be slowed down, or you increase evaporation speed so that you can quickly evaporate the solvents, and the matter in the liquid will be deposited on surface uniformly. So you can control that process. And so there's a lot of papers about this. One way to use this to our advantage is demonstrated by that paper. This one was published by one group in China. It's a really diluted silver ink you print on the substrate. You know, when you use inkjet printing, the narrowest line you can print is probably about 40 micrometer wide, because the nozzle we use typically gives you 25 micrometer diameter in the droplet. When you put on surface, it's roughly about 40, 50 micrometers. So that's 50 micrometer, for example. And when it dries up, using coupling effect, you know, all these nanoparticles in liquid will be pushed to the two sides. And you have two very narrow line with a pitch resolution of 50 micrometers. But this is very, using this one, you have very narrow line, but the conductivity, the conductance is limited because the line is really, really thin. But nevertheless, that's a way to use this phenomenon to reach high resolution printing. And so what we did in this, we faced a problem that when you print transistors, you want to have a very thin dielectric layer, very dense, pinhole free, so you can have a low voltage operation for your transistor. But when you print dielectrics, it's not really easy to get pinhole free, thin layer, right? So what we did here, we use the coupling effect. We print a dielectric layer, control drying process, and because the coupling process gives a very flat, because you see it's almost you can, I think probably this better. No, this is the first line. You know, when it dries up, we want to use this area as our pinhole free area. Because when you join the process, some particles may cause pinholes or some structure. You have a lateral flow of dielectric material. But our flows that will refill any pinholes you have, right? So the result is that you get a very nice, dense, pinhole-free dielectric layer. So we use the inkjet printing system and bought a PVP-based dielectric from Xerox. But by control the temperature, you'll see this is a printed, the profile of a printed dielectric layer. Okay, so we use 1 nozzle, 2 nozzle, 3 nozzle to print a different width of dielectric layer. Then control the drying process to control the width and the thickness of dielectric layer. Don't be fooled by this one, the product, because they are about 100 times difference, because this is micrometers, this is nanometers. So they are very wide compared, to the height you see here. And then you can, by control temperature and by control how much material dump onto the substrate, you can control the width of the flat area. Because of the lateral flow, and actually our yield, transistor yield increased dramatically because you don't face the pinhole issue anymore. Okay. So this is an example. Actually, this is printed the dielectric layer here. Very uniform dielectric layer for transistor application. And we use this process to fabricate different type of logic circuits so that you can have relatively more reliable process to make organic transistors. And also, because that you can gain very thin dielectric layer, we made the high capacitors, because normally when you make organic printed capacitors, it is very difficult to have high value because you want to avoid the pinholes, right? You want to get a thinner layer to increase the capacitance, but you got yield is very low. Because the coupling effect made the dense pinhole-free dielectric, we could make very high dielectric, very high capacitance capacitor. So that's one way. How we used this coupling effect to make a dense dielectric layer. Another thing we use the ink-substrate interaction is to make very narrow lines. As I mentioned before, when you inkjet printer, probably inkjet printer is one of the few technologies you can make a very thin layer. When you use flexo gravure printing, typical line width will be about 80 micrometer wide. There's some specific newly developed reverse offset that can go down narrower, but typically they use a very diluted ink. So it can make 1, 2, or 3 micron wide lines, but because they have to use a very diluted ink, so the thickness is very low, okay? But the total conductance of a line is very high. So what we did here is that we tried to use interaction of the inkjet printed line. So when you dump the ink, you got 50 micrometer wide lines, but we shrink it. So the nanoparticle in the ink would go nowhere, but forms a high aspect ratio line, so become almost like a cylindrical line. Because you shrink it, so the total metal amount in the line is higher than the reverse offset can print. So we get a very high conductance line. How does that work? Is that we have an ink with a 3 composition solvent. We have ethanol is really to wet the surface, and you have ethylene glycol in the middle. So when you had ethanol in it, when you print, you hope the ink will stay wet substrate properly, well-defined line. Then you heat it up, okay? During the kneading process, the solvent will go away. The ethanol will go away first. And then the surface energy of ink increases gradually. So what happens is that they will start shrinking, right? It will go narrower, narrower, narrower. At the same time, the ethylene glycol has some dissolve capability towards SU8, uncross-linked SU8, this layer. Okay, the blue, yeah. And the dissolved SU8 slightly, there's an interlayer between the printed silver and SU8. Now, they're floating. And the ethanol keeps evaporating at the 2 ends. And you have relatively high surface tension here and there. They pour the liquid out continuously and gradually, and also the ethanol will keep evaporating. So the line will keep shrinking during the drying process, become smaller and smaller. Okay, so that process can reduce the 50 micron wide line down to 4 micrometers, but the thickness increases, right? So when you look at the cross-section of the total cross-section of the line remain unchanged, but they just put the width to the thickness of the line. And that is one way to make high-resolution printing or extremely narrow lines. But the narrowest the width of the line will be determined the initial amount of ink you dump on the substrate. And of course, we designed another technology is that you have to drain the material. You can take the material away from this line. Then you can get even narrower line. But that's one way I want to show is that we can use interaction of the ink solvent and substrate to our advantage to make some features we want to make. Another thing that how to make a very narrow channel for transistors. Because when you print two lines, when you make transistors, you want to make the channel short channel, very, very close, because the mobility is terrible for organics. I mean, the maximum 10 now, so they are still very terrible material when compared to silicon, right? Or in a phosphide. Their mobility is terrible, so we want to make the channel really narrow. How to make them narrow? When you print two metals line together, the solvent in the metal line will evaporate. That basically primed the surface in between the two metal lines. They will have the same surface energy, the ink will just merge together. So how to make extremely narrow line is one challenge in printing transistor. What we did here is that we use a cross-linked SU8, and the solvent in our ink can dissolve slightly tiny amount of SU8 and form ink bank. And they push that towards the side of the ink job and then form ink bank, actually. We can reproduce this channel very reliably and down to 2 to 3 micron channel length. Anything below that, you have to do another formula. You can make that, but the surface becomes rough. So they are not very suitable for transistor application. But for 2 to 3 micron channel length, it's very reproducible. So by doing that process, we add interlayer, use this slightly dissolved SU8 as bank material. You can well define the channel length down to 2 to 3 micrometers. And this is the transistor output curve, from this transistor. And another challenge in printed electronics or for making transistor is alignment, as I mentioned that. Even the best machine we have at NRC now is plus minus 10 micrometers from layer to layer. So that means the channel you want to make, you need to make at least 20 micrometers, right? Or you print a huge, really wide gate electrodes to cover your source and drain to avoid missing the channel area. But when the transistor speed will be suffering if you make too much overlap between the gate source drain electrode with the gate, because the overlap capacitance will increase and your device will slower. With a with a low mobility, the device will be really, really, really slow. So how to do that? How to make this case? I want the gate sit right on top of the channel with a minimum overlap between source and drain, but not miss. If you're too narrow, then you don't have the field effect anymore. So there are people developed the process in Europe, and Paul Finger's team, they did a lot of work on self-alignment process. The idea is to align using a photolithography process to align the gate metal with the source drain electrodes, okay? Basically, you make using nano imprinting process to make a highly well-defined gate first. And then you put dielectric on, put a photoresistor, use a laser process to define a photoresistor area, okay? Then you evaporate gold on top of it, then lift off, there you have a well-defined source drain on top of the gate. But that process, you need a vacuum deposition. It's a very complicated process. Very elegant, but difficult. It's not compatible with printing process. Now, we look around and say, okay, why don't we use a nano silver ink combining with the photonic sintering in a similar way as people use as a negative photoresistor? Because in nano silver ink, there's we call a critical sintering point. When you use a pulse light to cross-link these, to sinter these nanoparticles, there's a critical sintering point, above which point these nanoparticles are sintered. You cannot remove them anymore. But below that, you can wash them away like usual ink, like nanoparticle ink. So what we did, we printed the source drain electrode first, put all the device material you want to put, and print a silver nanoparticle layer on top of it. Now, then through the bottom, we use a photonic sintering process to expose this area to the critical sintering point. And anything outside of this area are not sintered. So you can wash them away. By the end, you have a perfectly aligned source drain system, source drain gate system. And these are the samples we practiced. And now we can go down probably 4 or 5 micrometer gate length through a self-alignment process. But the system actually, the process is very, the ink is very, the process is very, need a lot of tuning, control, but that gives us a way to make a self-aligned transistor. Okay, so through this process, we have been able to make transistor arrays, up to 400 transistors together, different type of logic circuits, from very simple one up to the D flip-flop structures. But I have to be honest with you, these are the demo devices, right? You do lots of, but the fact is that during the printing process, you still have variations. The biggest problem in printed electronics, you can make 100, 1,000 hero transistors, but they are really they are heroes. So they are not identical. But what you want to do in the circuit design, you want to have identical devices. So it's very difficult. Or when you look at the paper, people publish paper, they have mobility, wonderful output curve, But when you look at details, even the neighboring transistors, they are not the same. We tried our best. We cannot control the variation below 15%. It's very difficult to design a proper circuits because you never know what will happen. We thought about using voting transistors to increase the accuracy, but the voting transistor need to be very, very reproducible. But we cannot go beyond lower than 20% variation. So, and also we also worked on printed organic solar cells. It is relatively reasonable actual product to use printing technology. What we did here, we developed a zinc oxide nanoparticle ink. That one does not need high temperature annealing. So when you put down, they form a dense zinc oxide film, and will not be dissolved by the solvent we use for the active layer. Then we developed a vanadium oxide, also printable thing on that. So using the printing process of Flexo and the slot die coating process, we made different type of solar cells. Here is a solar cell we developed for MW Canada for their automated blinds. Because what they want, they use the solar cell, this should be facing outside, to charge a battery. And so when you go home, you can use the remote control to raise or lower your curtain, right? And that because they need a flexible solar cell in the back. And this one serves the purpose. So the point I want to make is that when you look around the printable electronics, we went through really a hyper stage. We think everything can be done by printable electronics. We talked about the printing millions of RFIDs for the supply chain, but it's not there. The problem is that if you want to make ISO compatible RFIDs, the memory required, you don't even have the space to print these memories on that critical size antenna area, right? So it's a difficult process. So, but printable electronics indeed has its advantages, like large area flexibility, right? And what we want to look for applications is we want to look for applications that requires low resolution and does not asking for very high precision. and reasonable performance, okay, not super good, okay, and require reasonable lifetime. So if we can find application like that, what we are chasing sometimes is unfair for printable electronics too, because we have this silicon electronics thing in our mind. Constantly compare our device performance with a device fabricated in nanofab, like super clean room. So they are not the same because you didn't put the same amount of money into it. And they are so different beasts. So we need to find the right application. So one application we think it will be interesting is the energy harvesting area. Because when you do energy harvesting devices, a lot of them need to be flexible, mechanically foldable, flexible. And then the energy generation is typically proportional to the device area. So you need to have a large area. And in a lot of cases, don't mind the performance individual, like each action. For example, if I have, I'll show you a piezoelectric device. When you fold it, you generate 50 microwatts. Or next time you fold it again, you've got 40 microns. Who cares? Because you want to integrate this amount into a capacitor, use the average output later on. So you have very large tolerance towards those errors. And also all these devices, like when you print, organic transistor has terrible tolerance towards dielectric thickness variation. When there varies a little bit, the output will be totally different, right? And or the gap, the channel length variation, they're so sensitive. They're all good. You can all, when people publish these devices in Nature Science, I'm pretty sure they pick up the one or two from hundreds of transistors. Among the best, probably they are all good, but they can pick up a few of those, right? But they are not the same. So with the wide application of those small sensors, IoTs, and it's predicted that we will use, and right now we probably have 20 billion devices around the world, all linked, right? And each device uses a battery, at least a battery. And we think about if you change the battery, every time you have to change the battery, or when you want to use it, the battery is dead. So it's not really, first of all, it's not environmental friendly, and it's not convenient. What we want to do, all these applications, I'm pretty sure you know what those for. We want to provide a system. It will provide energy to this sensor with a wireless capability. And they will be there. Once you deploy them, they will always have energy or power in it. And then that's all. And so the reason we can do that, back 20 years ago, if I'm talking about using thermoelectric or triboelectric electricity to drive sensor, people think I'm crazy. But because in the past 22 decades, the power consumption in silicon electronics has dropped so much, we are talking about 100 microwatts now for a device, right? So all these mechanisms used to be, people thought they were useless. Now suddenly it become useful. And so we are looking at these devices using printing technology to make those type of devices to provide power to these sensors. One thing is the solar cell. We worked on carbon-based solar cell for almost a decade now. But when you look at the best ever device we made was like 7.1% power conversion efficiency. But it's laughable if you compare to silicon performance, right? But under the indoor light, like your office fluorescence lamp, they actually, the polycarbonate, because absorption and other device physics reasons, they are more efficient than polysilicon device. Okay, so the multicrystalline system and a polysilicon system, they will have about 5% power conversion efficiency under your office light condition. But the polycarbonate organic solar cell can produce about 16 to 17% power conversion efficiency. So they are way more efficient than silicon solar cells in your office condition. So why not use them to power a sensor system, right? So one project, here's here are the solar cells printed using our system, the flexible solar cells. So if you want to use them to compete with silicon, I think it's hopeless, except only for other very special applications. But indoor, they are better. This is one, like these devices, easily you can reach about 8 microwatts per centimeter square under indoor lighting. It's a very small power, but I'll tell you why. They are very useful, because a lot of Bluetooth chip now with a sensor, they only consume about 60 microwatts, right? So if you have 10 centimeters square of the device, you will be able to power that Bluetooth chip. And actually, this is one product produced by Webicom in Montreal. And their Bluetooth chip consumes 60 microwatts. Okay, it tells the temperature and the humidity in the room, talks to you through your phone. But in their system, there is no power management system. If it lights out, the device is dead. But nevertheless, the power is enough to have this signal. What we did here is we made a critical size light intensity detection for high performance building. So here you use solar cell, and solar cell current also used to monitor light intensity. So and we have a super capacitor in the back, about 0.3 farad. So we put that into a system, into a room. It measures light. Every 5 seconds, it sends a signal to a computer. Say, okay, this is light. Is that too strong or too low? The computer will decide if to lower the light, or because there's a lot of sunlight, they want to adjust indoor lighting. But this one does the work continuously. And during night, you switch off your office light to go home. It will use the energy stored in the supercapacitor. Over the night, it will use about 20% of stored energy. So we'll come back tomorrow morning, you see about 80%, 75 to 80% remaining power in the capacitor. So in that sense, you do not need to change this battery forever. We have about 45 sensors now in NRC's high performance building. They have worked since last July, and they're still sending data. And the data range is actually it's longer, it's further than we thought. Right now, typically we say 300 feet data distance, transmission distance, but way more than that. We have sensors on the third floor, on the second floor, we still got data. Okay, so this is one thing to power sensor. Another thing is thermoelectric. And we are working with a company in Europe, in Japan, develop thermoelectric generators. The idea is to use 5 to 10 K temperature difference to generate electricity. And these devices generate about 4 or 5 micrometer per centimeter square with a 5K temperature difference. And of course, there are lots of applications for this. You can think about the hospital environment, temperature monitoring, etc. And here, I think one thing in thermoelectric devices is how to step up the voltage. All these devices, no matter what you do, in the low temperature range, all these devices will output about 20 millivolts. The VOC is only 20 millivolts. And for those from silicon technology, you cannot even turn on the device, right? How to step up the voltage. So we developed a specific technology to convert these low voltage power more efficiently. There are some technology already out there from like a linear technology from Innocean, but our device is about right now, way more efficient than the things available on the market. Right now, I think we got here, old data, 44%. We got about 56% now, the conversion efficiency. So this is the printing process. All these can be printed. And the photovoltaic thermoelectric harvest the stationary energy, we call that. You basically put there, you don't move, you harvest energy, right? So what we are doing now, we want to combine the solar cell with the thermoelectric together. So if there's light, you harvest from light. If there's temperature difference, you harvest from thermoelectric. So we call it dual functional generator. And the other one type of device is mechanical motion, harvest motion energy. So one example is triboelectricity generator. Triboelectricity is kind of static electricity, right? When you pull off your sweater, you get zapped because there's a charge transfer between two materials. So once you have a charge transfer between two materials opposite sign, basically they are capacitor. So when you move two charged plates, basically you change the capacitance. And then because you're varying the capacitance or distance between the two plane charges, you will generate current. So using that process, you can generate electricity. Right? I mean, here is a list of materials. Like you have the material will tend to take positive charges. Some material will take negative charges. When you put two opposite materials together, you form the device. So it's really, really simple device. And so one typical simplest example is just you have developed a circuit. Okay, each time when you move the two plastics apart, put them back, you see you can integrate this voltage to form a stable DC output, right? So you see that the LED is lit up because you have a stable DC output, okay? And so the basic action is like between, you can make a device, a PET and Teflon. These are just like two layers. You just push them, right? And you have electrodes, you see the power, the output. And so by this, if you have the repeating action, you can generate certain amount of electricity. How to use them? I don't want to go to too much detail. I think my time will go up soon. And I just want to show you a few examples. This we call the tribal norm, metronome using triboelectricity. Okay, this is basically two pieces of plastic. And you will see my. I don't know if I have a sign. Sorry, I have to turn on the volume. So what's the big deal about this? Actually, a lot happened during that process. First, I'll show next one. So basically, it has a quite complicated circuit inside, right? You start nothing, you just tap the thing, you start to generate static charges or the charges in your circuit and stored into a capacitor. And then it's a judgment circuit to say, is there enough energy to turn on the following electronic circuits? If not, it just sit there. Wait, you keep tapping, okay? You have to work on it. Once it feels, okay, it's enough energy, I can turn on the circuits now, then switch on the electronics, read the resistor, and set the period of the metronome, okay? And then convert the digital signal, start the digital oscillator, and generates the beep in the sound and in LED. So there is not enough, a lot of energy in it, but nevertheless shows that it is usable. If you are really desperate in some situation, you do not need a battery, right? You have this in your uniform or somewhere, you can use it for some applications. And another example is just the two vibrating plastic surface, right? You will see the voltage keep increasing. It can go up to 13 volts. Okay. So just imagine different type of use cases, right? Another device we are working on is using piezoelectric device. a lot, I'm sure you all know the piezoelectricity, right? So when you bend it, or you stretch it, or you squeeze it, because you are changing the dipole moment, so you have different charge amount on the electrodes. That action, because the periodic change, you generate current again. So the simplest example is a piece of plastic with a piezoelectric in it. So once you just flip it over and over again, you generate, actually you can generate a reasonable amount of electricity in the circuit. The way is you need to find a mechanism to use it, okay? One thing, interesting part is e-paper display, right? E-paper display almost use very little energy. But each bend, when we bend one device, single layer device, we generate about 0.5 microjoule energy. But this energy is 3 times as much the energy required by e-paper, 1 centimeter by 2 centimeter area, e-paper display, right? So you see, like, as we bend once, it will turn on AEP sign, the Advanced Electronic Photonics Research Center. When you bend again, you erase it, okay? So it's a tiny amount of electricity. And now a lot of company wants to use that as a security sample, because we can integrate this with the e-paper. Once you open it, the film becomes black or becomes red or whatever. The sign is there, right? And it's not reversible. You can make that non-reversible. So this is something you require. It requires a little tiny, very little electricity. But you need electricity in order to do that. But PE cannot do the fancy jobs. But they may be able to find some application in those low end of applications. Another example is that friction. We can use a small drug box, right? So when you open it, it will record you open it already. So this indicator, e-paper indicator. When you open one box, it shows like Monday is open or Sunday is open. Basically, that's, you can remind you if you take
Sunday. Open, close. Monday, open, close. Tuesday, open.
Yeah.
Close.
So basically, that's repeat action. Basically, those a simple bending, flipping, you will be able to generate enough electricity for that type of action. The reason for in future many applications we just need an indicator or signage system. You do not need to have a lot dynamic display, but you may not need that for months, right? But sometimes you need this signage to show up, and then you need something, non-battery based power unit for that application. So. Yeah. So what we are thinking that we think that printable electronics, that's one area. Instead of focusing on printing the transistors, make fancy circuits, next step for real application is probably the energy harvesting device area or sensor. Basically, the printable electronics is really good in energy harvesting area for small amount and for sensor area. Because for sensors, typically you need a larger area or need to have a matrix to compare, because a loss of recognition is not unique. You need to have matrix to differentiate different type of possible species in the detection process, right? And there's a strong demand on printed sensors and printed power supplies for first responders. On their uniform, they require a lot of sensors. And so right now, these units are they integrate all commercial products together. By printing, you can print a much better form factor, device with better form factor on these uniforms, right? So these are the potential applications for printable electronics. So anyway, that's the end. So in summary, and I think printable electronics really still a very good research area. Lots of things to work on, especially for academic researchers, right? But we have to realize its pros and cons. We find the right application for them, and so that will be a bit probably a right way to pursue research in this area instead of exaggerating the possibility of PE. By the end, you cannot deliver. The funding agencies just get fed up. You guys say that every year. Why? The 5 years. I remember in the ID Tech EX, they give these predictions. I joked with them. I said, you guys just shifted the axis, time axis always shift back, right? So you will say, in 5 years, I'll get this performance. The problem is 10 years past, you're still shifting that damn curve. So but the real thing is that we'd better to look at really objectively what are the pros and cons of these material devices and how can we use them as is, right? Find the right application for them. So in some applications, we see the possibility of using this printing technology. Then we can say, okay, now these are the real technology. You see, we told you we can do this, but we think next 2 or 3 years you can do another thing. So that's the way we can advance our research, right? So that's really the way we are trying to do at NRC. And hopefully, I think that, I summarized PE in a positive way. And if you find anything interesting or if you find something we can collaborate, that'll be great. And I'll be super happy to work with you guys. And I have to give all the credit to my colleagues. And right now, I'm almost a salesman to sell the project to get funding. But my colleagues did all the work. Thank you very much.